And you'll see a little message that says that the recording has begun. Now, last time in class, we were up to the specific heat of water, and we said that water takes energy to heat up, it takes energy to cool down, and therefore we can attribute a quantity of energy called the specific heat, which is related to how much energy it takes to take 1 unit mass of water and heat it up by a certain unit of temperature. So for instance, the specific heat of water is 4.186 joules per kilogram. I'm sorry, per gram. If you want the SI, it's 4,186 joules per kilogram degrees Celsius. The unit of calories actually based on the specific heat of water. It takes 1 calorie to raise 1 gram of water by 1 degree Celsius. So that specific heat, it takes energy to heat water up. We release energy when we cool it down. Now, why doesn't this one advance? Okay, I've got my little, now I'm getting this. Now, the other form of energy we want to talk about is this idea of latent heat. Now, latent heat is similar to specific heat, but latent heat is the energy that it takes to go from one phase of matter to another phase of matter. So for instance, let's say that we have the 3 phases of water. We have, over here we have ice. Right here we have liquid water, water, and then we have steam over here. Or more properly, vapor, water vapor, okay? So if I have an ice cube at 0 degrees Celsius, and we add heat to it, it's not going to change its temperature, okay? Initially, it's going to just keep going from solid to liquid until it's all gone, okay? It's going to remain at 0 degrees because instead of the energy going into the temperature change, now the energy is going into changing the state. So we're going from a solid to a liquid. Now, once we're at liquid, we can add more energy. Now we have to heat it up to 100 degrees Celsius because it would be liquid from 0 degrees up to 100 degrees. So that would be the specific heat being added. And now once it's boiling, we can add a little more energy and it'll go to the vapor phase, the gaseous phase. And again, that takes latent heat. Now, what's incredible about water is water takes in a lot of energy to change from one phase to the other. And like its impact on climate, the specific heat of water has a big impact on climate because the oceans can store a tremendous amount of energy. The latent heat will have a similar effect. So, oh gosh, this is so difficult to advance. As we heat water up, we can use this to actually cool different systems. In the science building, we have a chiller on the roof, and what the chiller does on the roof is it sprays a mist of water, turning the water from a liquid into a vapor. And to do that, that takes energy. So it actually takes energy out of the cooling system. It actually puts energy from the cooling system into the air in the form of latent heat. And what that does is it actually makes a very efficient way of cooling the science building without expending as much electricity, okay? We also see a similar thing happen in the automobile. Now, for internal combustion engines, they generate a tremendous amount of heat, and this heat can be removed through the radiator. Typically, water, which is mixed with antifreeze and some other chemicals, is circulated throughout the engine to take the heat from the hot engine and dump it into the outside atmosphere. However, it actually has a safety feature. If the water gets too hot in the cooling system, it will actually begin to boil. And this latent heat will actually give you a little time before the engine completely overheats and damages itself. So when you see your radiator boiling over, that's actually the water being converted into gas because your car can't get rid of the heat fast enough. And that's getting rid of the excess energy that could be damaging your engine. Of course, if you boil away all your coolant, you're going to be in a lot of trouble because that engine's either going to shut down or it's going to get damaged. So the newer engines do have protection. So again, latent heat is very important for this. Now we're getting out of the hurricane season. And if you know anything about tropical storms will form over warm water, but they die out over land. Now, why is that so? Well, the reason is actually very, very simple. Think warm water, right? When water evaporates, it puts energy into the atmosphere. Okay, so energy is transferred from the ocean into the atmosphere. Now, this energy can then be used to power the storm. In fact, all this vapor from the evaporating water goes high into the atmosphere where it condenses into rain. And as it falls, it converts potential energy into kinetic energy, and this becomes wind. So a storm, like a hurricane, can produce a tremendous amount of damage because all this latent heat from the warm ocean or the warm water is being transferred up into the atmosphere where it can get these winds going. As soon as it goes over land, there's no more latent heat. You don't have a lot of water that can evaporate and go into the storm. We, of course, use water vapor to cool off. We can actually see in a respiration that our breath is almost 100% humidity. So when we breathe, we are not only evaporating water into the atmosphere, we're also giving off heat. Now, here's an extreme case where somebody is, this is probably in the Arctic or the Antarctic someplace, they're giving off their breath, which normally is invisible, and it's condensing immediately into a fog, a cloud of aerosol particles. And this just demonstrates that water vapor is always there. We're always breathing that out. Me more today than usual. But it's only seen when we have that hot breath condense on something cold, like you can blow on a cold window, or if it's cold enough, your breath will actually become visible. Now, if you're a dog, you have no ability to cool yourself other than to breathe. So what you notice is when dogs get very hot, they tend to pant, and that's basically they're taking the water in their mouth and they're blowing air over it to quickly evaporate that and take the heat away. So that is a demonstration of how latent heat can be used to cool our bodies. Now, we are not dogs. We actually have another source of cooling, and the sweat on our skin will actually evaporate into the atmosphere. And when it's hot out, we can get rid of excess heat as this water goes from liquid to a vapor form. And that takes energy. By the way, if you want to know how much latent heat water has, it has over 2 megajoules for every kilogram of water that you evaporate. So your body can actually get rid of 2 megajoules of energy. 1 kilogram of water is roughly about a liter for every liter of sweat that you evaporate. Now, when it's hot and humid out, you've got a problem. You're trying to get rid of this latent heat. If it's a dry heat, this can this water can evaporate right into the atmosphere and you can cool very rapidly. However, if it's humid out, the humidity causes the water to recondense on your skin. So as quickly as you get rid of the water vapor, it's recondensing and or it's having trouble evaporating specifically. And that's why when it's humid out, it's very difficult to keep cool. So what happens with the humidity is, when it's a very low humidity, like 20% humidity, the water will evaporate very quickly off your skin. It's very easy to cool down. When it's around 50% humidity, it starts to feel a little less comfortable because any sweat that's on your skin is going to evaporate at approximately half as quickly as it would if we're completely dry out. And of course, at 100% humidity, your sweat's not going to do anything to cool you down. And that's why when we talk about the heat index combines temperature, okay? The hotter it is out, the more you need to cool down, or the more difficult it is for you to cool down, and humidity, because increasing the humidity, I know that doesn't look like humidity, increasing the humidity makes it more difficult for your body to cool. Here is how we actually put this water on our skin. We, of course, have these sweat glands. The sweat glands will take water from our bloodstream. The water will simply, the water will simply come out of our blood through osmosis into these sweat glands. And not only does the water come out, I apologize. It will also carry with it electrolytes. So as the water diffuses into the sweat gland, it goes up these sweat channels, and two things can happen. If your body is in a high flow state where it's putting a lot of sweat on the surface of your skin, your dermis, which is the lower layer of your skin, will not reabsorb this moisture. If you're in a low flow state, like let's say it's cold in the room and you don't want to cool your body off, your dermis will reabsorb this, okay? So there's your body's cooling system. Not only do we breathe to, give off water vapor, we evaporate through our lungs, we also sweat. And again, it's a process of turning, something from a liquid to a vapor, which takes energy. And here we see just how much latent heat. I know this is a little hard to read. There's a latent heat of vaporization for water, and it's 2.26 megajoules per kilogram, okay? And mega, of course, means a million, all right? You do get latent heat from water, okay, when you melt ice. It's not quite as much, but everybody likes an ice cube in their drink on a hot summer day because it keeps that liquid cool. When it goes into our body, it cools our body. So if we look at this, the amount of latent heat from melting an ice cube is about 1/3 of a megajoule for every kilogram of ice that melts. So there's another example of latent heat. So just to summarize all this, again, specific heat. This is a measure of how much energy it takes for a temperature change. Okay. So obviously, when we heat water up, it takes energy in. When we extract energy out, it's going to take, it's going to drop the temperature. And of course, if you live near the shore, we know that specific heat is very, very important in keeping the temperatures very moderate. Latent heat is when we change phase. We go from solid to liquid, like we're melting, or we go from liquid to solid when we're freezing, from liquid to vapor when we're evaporating, or from vapor to liquid when we're condensing. And again, there's a latent heat of fusion, which talks about going from solid to liquid, liquid to solid, or vaporization for liquid to vapor, vapor to liquid. All right. So that is basically energy stored by different substances, how it changes temperature, how it changes state. Let's talk about how we can transfer heat, okay? There's much more detail here in this chapter that I necessarily want to dwell on. But with winter approaching, we can see how heat transfer can be very important to keeping our homes or apartments or dorms a comfortable temperature, okay? So let's see what's going on here. Basically, we define 3 different ways which we can transfer heat from one object to another. So you want to heat up your room, okay? You can do it through convection. That would be, for instance, like a radiator, okay? You can heat it through conduction. Radiators also conduct heat to the surrounding air, but they use a combination of conduction and convection to help warm things up. Or you can use radiation. You know, think about, for instance, like an electric heater will shine infrared light to heat different things up. But those are the 3 basic ways that we heat different objects up. Now, conduction is not very efficient. Conduction, think about it this way. What are we doing when we're doing conduction? We are adding heat to one end of a substance, right? The molecules or atoms are colliding with one another or next to one another. That transfers heat to the next row of atoms or molecules, which transfers to the next, which transfers to the next, which transfers to the next. Conduction is very, very inefficient for most solids, okay? And that's good because if you have something that's insulating, that allows you to pick up something that's hot, but have some sort of insulating barrier that doesn't conduct the heat very, very easily. So something that is a poor conductor is known, oops, made a mistake there, is known as an insulator, okay? We've heard, you hear of electrical insulators and thermal insulators. And basically with an insulator, there's no free electrons. So things that are good electrical insulators are also pretty good thermal insulators. They don't transfer energy very easily. So conduction is one way that we can move heat from one object to another. Now, metals are great conductors. They can have a large number of electrons that can bounce it back, okay? In a metal, think about, here's a bar of metal. If I add heat to one end of the metal, okay, instead of the energy going from atom to atom, there are electrons in the metal, and the electrons are whizzing around at very high speeds. They'll take the energy in the form of kinetic energy and transfer it very quickly to the other side. So if you've ever put like a metal spoon in, you know, a hot pot of water, you notice that if you leave it in there that long, it becomes hard to grab the other end. So normally, with a lot of cooking ware, they'll have a plastic or wooden end attached to the metal. You don't want to conduct the heat and burn yourself. Okay, yeah, try taking a cookie sheet out of the oven after it's been in there at 350 degrees Fahrenheit. You want to have some type of barrier there, you know, to protect your hands when you lift that up. Okay, we won't go through the conduction equation. That's not really something that we want to talk about too much here. But what we can see here is how different materials will conduct energy differently. Think about this constant K as just, relatively how well energy is going to go from one end of an object to another end. All right, so silver is a very conductive material, and obviously it conducts heat very, very well. Okay, copper is good. Copper and silver both conduct electricity very well. They both conduct heat very well just because of those electrons. Aluminum, almost as good. Okay, so all of these you probably don't want to use, in terms of making cooking utensils. Like silverware used to be very popular, where people would make spoons and forks and knives out of silver. They still do. But one of the big problems is if you put a silver spoon in a hot dish, not only is silver very expensive, it's going to conduct the heat, and you can get burned pretty easily. So if you look at cooking material today, most of our cooking ware is actually made out of stainless steel. Notice stainless steel, wrong thing right there. Stainless steel has a relatively low conductivity for metals. Okay, it's not all that conductive. So it's conductive enough to take the heat from a burner or from a heating element and heat up whatever inside. But it's not so conductive if you take a stainless steel spoon and put it in, some pot. It's not going to conduct the heat instantaneously. Now, for our homes, we don't want to conduct the heat at all. Okay, if it's cool inside, we want to keep it cool inside. If it's warm inside, we want to keep it warm inside. We want it cool in the summer. We want it warm in the wintertime. So, buildings made out of concrete, okay, and made out of, brick, glass windows, the conductivity is moderate. It's not great, it's moderate. So if I try to heat my home with just this on the outside, I'm going to lose a lot of heat, to the environment, okay? Or I'll have a lot of heat come in during the summertime. So what we do is in our homes, we add something called insulation. Fiberglass insulation is a great example of a material which is mostly air, which won't conduct heat very easily. It has fiberglass fibers, just as the name implies, and this prevents heat from conducting easily inside and outside. So in a well-insulated home, you will lose very little heat to the outside during the wintertime, and you will gain very little heat from the outside during the summertime when you have the air conditioning on. Okay, so you'll see, if you're trying to insulate your home, there's something called an R value. You can go to Home Depot, or you can go to Lowe's or whatever home store that you go to if you want to fix your home yourself. And they'll have like different rolls of insulation. And they'll have R and some number. That tells you how good the insulation is. It tells you for a given thickness, how conductive is it for the heat? How well does it insulate your heat? So R values are very, very important to making sure that your house is energy efficient. So again, if you live in a concrete structure, you live in a brick structure, both of those don't have great R values. Even wood shingles aren't great for keeping the cold out in the winter and keeping the heat. Keeping the heat in the winter, keeping the cold in during the summertime. But better R values can be obtained by using such materials as styrofoam, fiberglass, And the thicker the insulation, the better the R value, which means you're not losing energy as much, and your heating bills and your cooling bills are not all that as much. So for our region, region 2, you can see that they want attics insulated to R49. That's really a lot of insulation. Walls should be R22. Exterior basement R15. And that's just to keep the heat from transferring inside and outside. So if you're heating your home, you're not spending more money than you need to. Okay. And this is what fiberglass insulation looks like. You can see here that they put it in between the, these are called wood studs, and basically they help support a wood framed house. And it's very convenient. You just put it right in between each individual board, and that creates a thick layer to protect you. It's like putting a coat on your house, if you will. And depending on what kind of structure you're in, the more insulation you use, sorry, folks, the more insulation you use, the more energy that you save, and the less your heating and cooling bills. Now you can see here some of the problems with a house. Okay, this is a thermograph, and we can clearly see that they did a real good job on the roof. The green indicates cooler, which means you're not losing as much heat through there. A little more heat is lost through the walls, but by far the greatest amount of heat is being lost by these windows. So in terms of designing a house, or designing an apartment, or designing a building, one thing you've got to be very mindful of is windows are the really weak point in heating and cooling. And I'm somebody who loves sunlight. I love natural light coming in. But the problem is windows are not only expensive, but they are a great way to lose energy into the environment. So what we've tried to do is we're designing the windows better and better to retain the energy. If it's cool in, we keep the heat from coming in. If it's warm out, if it's cool inside, it's going to be warm outside. If it's warm inside and cold outside, we want to keep the air in. Now, glass is too good of a conductor of heat to be practical in the single pane. So what we actually do now is we create windows. Look at some of your windows sometime. If it's a recent construction, they'll put a little air gap between two plates of glass. And this allows a thermal barrier that prevents the heat from easily coming in and out. In fact, in really good windows, there'll be triple pane windows, and those are much better at retaining the heat. There's something called a thermos bottle, and these take into account conduction, convection, and radiation. So what they do, first of all, is to eliminate conduction, okay? They actually create what's called a dewar, and this dewar is this hollow cylinder, okay? It's this hollow walled cylinder, and they either make this out of steel or glass. And there's a vacuum here, so there's no air to conduct energy. So that's a vacuum, which means the absence of anything. So heat can't transfer from one wall to the other wall through conduction. Also, there's no air there, so there's no convection. And then finally, they silver the surfaces. They make the surfaces shiny, so thermal radiation will actually bounce off the walls and not go from one wall to the other. So if you have one of these thermal bottles, these thermoses or these dewars or whatever they call them, you'll notice you can put a cold drink in them okay? And they'll remain cold all day long. They'll remain cold all day long. Or you put a hot beverage in them, they'll remain hot for, like 24 hours. Really very efficient in keeping, things warm or cold. Do you ever wonder why radiators are shaped the way that they are? The old style radiators or the portable, uh, or the portable uh, electric heaters have this like this grid type uh, structure to it. And the reason for this is because this is set up in such a way that it pulls the air into it. I don't know, it just happens, my thing here. Pulls the air into it, the cold air, okay? And then as the cold air comes into these fins, it will heat up and leave the structure as it goes up here. It's getting warmer and warmer and warmer. It'll leave the structure as warm air, okay? Because it's buoyant, it weighs less, and that'll pull even more air into it. So you don't even need a fan to transfer the energy from this hot structure. So in the old steam radiators, in the hot water radiators, or even in these electric radiators, they all will produce moving air without any moving parts. And it's all done through convection, through basically transferring the heat through these large surface areas. So I guess what I'm trying to say is there's a lot of surface area here with these radiator fins, the way this is designed. Okay, moving on. Again, convection is how storms are powered. Warm, moist air rises, it goes high into the atmosphere where it condenses, and then it drops down with cold air. It's cold air with rain pulling it down. Even our weather is powered by convection. Convection cells cause the warm air to rise, the cold air to sink, producing these big convection cells in the atmosphere. Because the Earth spins, the Coriolis force causes what should be air going north and south to actually go east and west. And also convection. We see convection in ocean currents. The Gulf Stream is a very famous ocean current, which transfers energy from the mid-Atlantic and the Gulf Stream, the Gulf of Mexico to Europe. Europe is actually much warmer than it should be due to this transfer of heat, which comes from the Gulf Stream. And just to give you an example, we are the same latitude as Spain, okay? But yet if you go to Spain, you notice that their winters are much more mild than our winters thanks to this Gulf Stream. Oh, there you can actually see a thermal view of the Gulf Stream. Convection also drives plate tectonics. You can see that the mantle is actually driven by this too. All right. As we get closer to winter, we are using different clothing, and there is actually a tremendous amount of engineering that goes into clothing. What became popular, I guess, about a decade ago is this new, it's not new anymore, is this thermal fleece. This has been a very effective type of clothing in cold weather, especially for athletes who tend to be active and then inactive. I do a lot of running, so I wear this fleece in the wintertime, because when you're running, you're generating more heat. And the way that this works is, and the way that even other high-tech clothing works is, when you exercise, you tend to produce more sweat, right? And unfortunately, when you sweat, that gets your clothing wet. So you work out and then all of a sudden you stop, and now all of a sudden your clothing is wet. That's not good because typically the clothing when it's dry is very good, insulating you. As soon as your clothing gets wet, it conducts heat very easily and you can get cold very easily. So this clothing actually allows the water vapor or the water from your sweat to be pulled out from the surface of your body, go to the surface of the clothing where it evaporates, and this fleece or other thermal clothing remains dry. So doesn't seem like much, but again, if you do any type of activity in the cold weather, you know that some of these thermal clothing is incredible in terms of keeping your body at the right temperature. Oh, thermal radiation. We lose heat to the environment through conduction, through convection, but we also radiate heat, okay? We radiate energy. Now, we can't see this normally, okay? What can our eyes see? Well, we're going to talk about this later on, but typically our eyes can see wavelengths anywhere from about 0.4 micrometers or microns, okay? That is 1/millionth of a meter. That's the size of the wavelength of light. And that wasn't a very good wave. All the way up to about 0.8 micrometers. It actually is more defined as 380 to 780 nanometers, or 0.38. But this is a pretty good rough estimation of what our eyes can see. What we radiate, the thermal radiation that we give off, is what's called infrared, okay? This is visible up here. This is what we can see. IR is too long of a wavelength for us to see. Our bodies tend to radiate right around 10 microns, 10 micrometers, which is far too long of a wavelength for our eyes to see. But what we see here is this thermal camera is taking an infrared image of somebody's body, and it's computer coding, it's digitally coding different temperatures to the amount of infrared light that it sees. So for instance, the highest temperatures correspond to these light regions, the lowest temperatures correspond to these bluer regions down here. So we lose a lot of energy through thermal radiation. So simply by wearing thicker and thicker clothing, what you do is you trap that thermal radiation in, you prevent conduction, you prevent convection, and that keeps you warm in the wintertime. That's why we put so much clothing on, thick coats on in the wintertime. During the summertime, we do the opposite. The more skin that's exposed to the environment, the more thermal radiation we can give off, the more we can cool down. Incandescence is actually glowing due to thermal radiation. And really hot things that are much hotter than we are, such as hot coals, okay, or incandescent filaments, are such a high temperature that they glow mostly in the infrared, but they also give off some visible light. In fact, different things will glow at different peak wavelengths depending on how hot they are, okay? And this is kind of cool. We can tell the temperature of something simply by the kind of light that it gives off. So if something is warm like us, but not all that warm, it's going to glow in the infrared. If something is hot, like a hot coal, it'll give off some red light, but again, it'll still mostly be in the infrared. Something's really, really hot, like our sun, it will glow in the middle of the spectrum, and appear to be sort of whitish to our eyes. This is a little more complicated than we'd like to go over in this course, but you can see right around 300 degrees Kelvin, that's where we tend to glow. So we tend to glow, right around 10 microns. A hot incandescent bulb will glow right around 1 micron, but an incandescent bulb does give off some visible light. And of course, our sun peaks right here, so that's why it gives off a lot of visible light. Again, at 1,000 degrees Kelvin, mainly infrared light, we can feel that from hot coals. If we're near a fire, we're near a barbecue pit. At 2,000 degrees Kelvin, that's an incandescent bulb. 6,000 degrees Kelvin, that's the sun. It glows mostly white. And if you could see in the ultraviolet, you'd be able to see the corona of our sun, which glows anywhere from a few hundred thousands of degrees Kelvin to over 1,000,000 degrees Kelvin. So different temperatures. The colder something is, the longer the wavelength, the warmer something is, the shorter the wavelength of how it glows. All right, folks, I'm running out of energy, so I just want to hit this last point right here. Thermodynamics. Thermodynamics basically says turning heat into movement or work, okay? So we're going to turn what we call heat. I don't know why they use a symbol Q for heat, but they do. We're going to turn that into work. Okay. Why is that important? Well, that's the whole principle behind a engine. Okay, engine works this way. We are. I'm going to have to end. I'm sorry, folks. My nose is now running like a sieve. So what I'll do is I'll pick up on thermodynamics next time. Again, the whole idea is with the heat engine, it's some type of device that's going to turn the thermal energy. Okay, and this thermal energy can come from combustion. It can come from heating a boiler up with wood, with coal, natural gas, with oil, and allowing that thermal energy to cause either a gas or a liquid to expand. As it expands, it's going to push on a piston, and this is going to do work. We know work is mechanical energy. All right, folks. I'm sorry. I'm not feeling great, so I'm going to stop the recording there. But hopefully we didn't lose